Hello everyone, welcome back to CpE 2301. We are now in Unit 5 Lecture 2 in your sequential building blocks. So for this lecture, we'll be discussing the asynchronous counters or the ripple counters. And then aside from that one is your decade or the BCD counters, and then the use of your 74x90 decade counters. So this is your IC that will be focused on this lecture. So what is a asynchronous or ripple counters? So it consists of a series connection of complementing flip-flops with the output of each flip-flop is connected to the clock input of the next higher order flip-flop. So what it means is that the clock inputs of your flip-flops are connected from the previous flip-flop inputs, or rather flip-flop outputs. So the term here is asynchronous. So if you remember, the distinction between synchronous and asynchronous is that the asynchronous part does not rely on your clock, but for this part of the lecture, it only requires a certain part of your, or the clock is required in a certain part of your circuit, but the rest is dependent on the other flip-flops. So the flip-flop holding the least significant bit receives the incoming count pulses. So this is the one who receives either the clock or the count pulses. So it's either you are the one who becomes the clock pulses with the use of a push button or a switch, or you supply a clock source. So this is an example of a ripple counter. So it's a 4-bit binary ripple counter. So based on the truth table here, that you can count from 000 until 1000, but since this is a 4-bit, so you go further 1111. So this is the equivalent timing diagram for the 4-bit binary counter. And then to illustrate this one in flip-flop form, so I will be giving you the example of the T flip-flop and also the D flip-flop. So on the left side here are using the T flip-flop, and then on the right side is the equivalent 4-bit binary counter using the D flip-flop. So let's first look at the T flip-flop here. So once you observe here is that the output of your T flip-flop from the A0 here, or the flip-flop A0, is connected to the clock source of the next T flip-flop, and then this flip-flop is connected to the next, and then here. So basically they are in a asynchronous clock source. So as a note here, all of the clock inputs are in falling edge. So as you observed here, there are circles or bubbles into your clock inputs. So which means this is all falling edge. So the time when the signal is from high to low. So when the signal output here is 1 to 0, so this triggers. Remember that the setup here is that the toggle or the T input here is logic 1, which means it toggles. So every time the clock pulse is from high to low or falling edge, it toggles the current value. And then we have here a asynchronous reset when we want to reset the flip-flops. To demonstrate this one further, I'll show you the circuit for this one. Okay. So this is now the equivalent circuit of your T flip-flop. Um, yeah, and then I have LEDs here to demonstrate the display of your bits from the least significant bit to the most significant bit. So since A0 here is our least significant bit, so I assigned here in this LED. And then the most significant bit is here. So I initially reset everything here. And then, so it is still 0. Then based on the given, the input of your T flip-flop are logic high or 1. So that's it. So every time my input here is from high to low, so this is initially high. So when it has a clock edge of high to low, so it triggers the toggle. So you have now your first count after 0, then high to low. So the next count, high to low, high to low. And then goes back to 0 after. So this is your T flip-flop. So basically it will be the same output scenario but different settings for your D flip-flop, since the operations of your D flip-flop isn't toggle but a set reset. So you have to analyze what will be the inputs and outputs of your D flip-flop. So for in this case, it uses the Q bar or the output invert of your flip-flops as your input of your next state. So every time it flips, so that's your inverting property using D flip-flop. Okay, next is your BCD ripple counter or a decade counter. So based on the term BCD or the decade counter, so you only count 10 numbers. So it's from 0 to 9. So you already know this one based on our previous lectures of the BCD. So below here is the timing diagram of your BCD. So every clock pulse here, so in this case this is still falling edge. So every time the clock pulse is falling edge, high to low, it triggers the next state. So this is 0, 0, 0, 1, 0, 0, 1, 0 until 1, 0, 0, 1, and then goes back to 0, 0, 0 again. So we have this one. So how do we design this circuit? So for this example, we'll be using the JK flip-flop. So first I create a truth table of your sequence. So this is just the simplified form I can show you so that you won't be confused between the present state and then the next state. So basically I am placing here the sequence in a table form. So from 0, 0, 0, 0 to 1, 0, 0, 1 until its next state is 0, 0, 0, 0. And then once we observe here is that the Q1 changes the state after each clock pulse. So every time the clock pulse from the previous timing diagram here, so every time it falling edge, so it toggles the output. So every time it is from 1 to 0, it changes the Q, sorry, yeah. So it toggles every time the clock high to low. So the JK flip-flop characteristic used is the toggle, so which means the JK values are 1 and 1 to create a toggle characteristic. So the clock input of this flip-flop is from the clock source or the pulse. So remember that these are 4 bits, so therefore there are 4 flip-flops to control. So this is the first flip-flop from the least significant bits. So we continue to observe everything here. Again, the clock inputs are still in falling edge. And then once we observe the Q2, the flip-flop that is oriented or based on Q2 here is that Q2 complements every time Q1 goes from high to low. So I highlighted the scenario where it is high to low. And then based on the definition here is that as long as it is from the Q8 is 0. So when Q8 becomes 1 around this time, Q2 remains 0 here. So we just observe here the characteristics of Q1, sorry, the Q2 with respect to Q1. So that's from 1 to 0, so that's toggle. 1 to 0, so it toggles from 1 to 0. Under falling edge 1 to 0, from 0 to 1. This is a toggle also, 1 to 0. And from here the next falling edge is from 0 to 0. So you have here 2 options. So either to use the reset function of your JK flip-flop or the unchanged, which is the 0, 0 value. So for in this case, I'm using 0, 1 as a reset. You will know later on why it is being treated as reset instead of unchanged. So since we use reset and toggle for this scenario, so we can now create the equivalent equations for your J and K values. So this is why I used the reset, because when K becomes 1 and 1, or 1 as is, so the value of your K is 1. So you don't need any other circuits related to this one. So you just have to have a direct input here. And then the value of your J here is from 0 to 1 based on Q8. So this is 0 for everything here is 0 whenever it is toggle, and then 1 whenever it is resetted. So the clock input from this flip-flop is based on Q1. So next is your Q4. So based on the Q4 here, it complements every time Q2 goes from 1 to 0. So from this point, we are now no longer checking Q1 as our reference point, but our reference point is now Q2. So though you have the same point here, it's from 1 to 0, but this is more a longer sequence of your 1s and 0s. So the time the value here is from 1 to 0, the value of your Q4 toggles from 0 to 1 and 1 to 0. So therefore, the JK flip-flop characteristic used for this is toggle, so the equations used is 1, 1. And then the clock input of your flip-flop is from Q2. So instead of Q1, it is now Q2. And then last flip-flop is from the Q8. So we observe here is that Q8 remains 0 here as long as either the values of your Q2 and Q4 are 0. This is based on the reference that Q1 is our clock pulse. So every time the clock pulse is from 1 to 0, Q8 is still 0. 1 to 0, 0, 1 to 0, and 0. So the only time it isn't becomes 0 is in this part of your table or the timing diagram. So Q8 complements when Q1 goes from 1 to 0 when both Q2 and Q4 are 1. And then Q8 is cleared on the next transition of Q1. So it's either you'll be using around here is to resets or a toggle from 1 to 0. So the characteristics used from the JK flip-flop is still toggle and reset or unchanged. And then at the same time I used here is still the same, reset and toggle. So the characteristic for your reset, K, the equation here is 1 to simplify the circuit, and then the rest of your flip-flops K value is still 1, so lesser logic gates to be used. And then here from your J, so there are two values to be accommodated, either 0 or 1 inputs. To create that one, the condition here is that every time our Q1 is from high to low, and then the input of your Q2 and Q4 must be 1, 1. So the equation used here is Q2 and Q4. So the time when this is 1, 1 and Q1 is from high to low, it toggles your input, rather the output of your Q8. So in summary, in the flip-flop would look like this. Okay, to illustrate this circuit, so this is now the equivalent circuit I have made. Run. Okay. Again, every time it is from high to low, it counts for the next count. Okay, high, low. Then after 9, it should be 0. It goes back to 0. Okay. Okay, so that's it. So this is now the example of using a BCD counter. So using this counter as, since this is a BCD, so it is counting as a 1 digit of your decimal. So when we create 3 digits or 3 decade decimal BCD counter, so it looks like it is part. So we use the value of your Q8 for the next clock input of your next BCD counter. So I'll show this one further later on the lecture after this. So after this one, you can go and so on and so forth on the left side here to have more than 3 digits, just continuing the sequence of this circuit. So this is now your 74LS90 decade counter. So again, this is a decade counter, so it only counts from 0 to 9. And then this is a asynchronous ripple type counter. So basically what we did previously here, this is what we created. So this is the example of your, or the internal components of your 74LS90. So remember that this is the pin configurations. So this is the actual IC. You have here 2 clock pulses. And then MR1, MR2, this is your master reset. So based on the table diagram here, is that whenever the R1 and R2 here is high, the value of your outputs are 0. And then MS1 and MS2 is master set. Some of your data sheets refer it to R91 and R92. Basically what it does is that whenever these 2 values are high and also high, the output of your 4 bits is 9 or 1001. Other than that one, when everything else here is low, R1, R2, S1, S2, or R01, R02, R91, and R92 becomes low, it counts the counter. So basically what it does here, it counts up. Pins 5 and 10 are your VCC and ground. And then pins 4 and 13 are no connection, so they don't have any connections. So you can leave that one as is. So this is an example of your decade counter applied to a default configuration. So basically this is your default configuration. So this is a decade counter or modulus 10 counter. So other examples here is that you can also design a modulo n up counter. So what it means is that whatever the value of your n here, so it counts from 0 to n minus 1. So for example, modulo 6 here, it's from 0 to 5. Modulo 100 is from 0 to 99, and then modulo 24 here is 0 to 23. So everything here is using an up counter. And then on this example, we are only using 74LS90 ICs. So first, here is the modulo 6 or 0 to 5 up counter. So first, you can either place here the state diagram, but basically we don't need in creating the state diagram for a longer modulo. For example, if it is from 0 to 100, so you can't create a 0 to 100 state diagram. So that's a very long states. So what we do here is using the reset function of your 74LS90 as the means of restarting the count back to 0. So creating the combinational circuit based on the last count to make it reset. So this is the example for that one. So again, the clock inputs here are, on my simulation here is rising edge, but on the actual circuit of your IC of your 74LS90 it's falling edge. That's why I added a inverter. So the keyword here is the last count. So the last count here is 5. So what can we do to make it reset when the count is 5 or after 5? But remember, this is after 5. We still need to show it is 5. To demonstrate this one, so I just link here that this is 5. So whenever the value of your Q0 and Q2 is 101, so or 11 here, it resets the value of your count. Okay, so this is now the equivalent circuit I have shown you earlier. So let's just demonstrate this one. So usually at first scenario it randomizes what the output is, since our reset is no longer available. You can either extend this one to make it more asynchronous reset. So that's 3, 4. Then after 4 it becomes 5. And then this is now the output. So the problem here is that whenever we use the 5 output here, it directly resets your count. So this is your asynchronous counter. So it doesn't wait for a clock pulse to reset. So what we do here is to look for the next count, which is 6. So I'll be using 6 instead of 5 as a point of resetting your count. And then just to add on here, to have a asynchronous reset, I'll be adding an OR gate. Okay, so I cannot flip. Okay, so we have now a asynchronous reset. So we can now reset at any point. So just for an example, we can now reset at 1. So 1, 2, 3, 4, then 5, and then when it is 6, the output must be 0. So there, 0. So therefore, the previous statement we have is incorrect. So with that, this circuit is no longer true. So what should be the word here to be used? So it should be last count plus 1. But just a note here is that not every counter uses this formula. So let's say you're using a rising edge, it might have a different approach in creating your counter. This is the example of your modulo 100 or 0 to 99 up counter. So remember that our BCD here, sorry, the BCD counter here is from 0 to 9. So we create another counter here to demonstrate the other decade, or the tens place. So 1s from 0 to 9 and 10s from 0 to 9. Remember that we want here is that right after 9 it goes back to 0. So whenever it's from 9 to 0, the output here is 1 to make the output 10. So you can either use this one. So whenever the values of your Q3 and Q0 is 1 and 1, you can start the toggling of your clock pulses of your second decade counter. So just to demonstrate that, okay. So what I did here is a simplified version of your of the circuit. So just to explain that, is that remember that the count here is from 0 to 9, and then after 9 it goes back to 0. So you no longer need another output here, because after 9 this becomes from 1 to 0. So again, our condition is that whenever the value here or the output is from 9 to 0, we add 1 to the tens place. So from 9 to 0 it toggles here from high to low, and then triggers the next output or the next count. So this is the asynchronous reset. So I just place it on as high to reset the counts here. Okay, and every time I toggle here from high to low, it increments. High to low, 5, 6, 7, 8, 9, and then 1, 0. And then we don't need to worry about 100, because right after 9, 9, it goes back to 0, 0. Just to demonstrate that one, I'll be clicking that one until 99. And then 98, 99, and then high to low, it goes back to 0, 0. And at any point you can also reset that one. So that's it for Modulo 100. Okay, so for the last example here is Modulo 24. That's from 0 to 23 up counter. So remember that 23 is a 2-digit number, so it's still the same as the previous one. We have here the tens and ones, but the condition here is until 23. So you can have here that the value here is 3, and then the value here is 2 to make it reset. Okay, to demonstrate that one, I'll also show that one. File open. So this is your Modulo 24 or 0 to 23 up counter. Let's have the reset. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16, 17, 18, 19, 20, 23, and then 0. Okay. As you observe here is that I using the 3 value instead of 4. So the difference between this one from the previous example is that we are controlling the clock. That's from high to low. So remember, what we want here is the condition high to low. So from 23, the transition from 23 to 24, so that's the time you goes back to 0. The problem from the previous example is that around here that we don't use the last count as our reference is that because the reset here is your asynchronous reset. So the time it receives the high signal, it resets back to 0. So that's the difference when you're controlling the reset function and then controlling the clock function. So that ends my lecture, and thank you for listening. So just note that everything here is simulated as your 74 LS90. Basically, they are not found in the simulator I found, but I modulated that one to make it more fitting as a 74 LS90. But if you're using Proteus, it would be the same output. So by the way, the part here is the 7-segment decoder. So you can use this one instead of creating the decoder itself to use the 7-segment. So that ends my lecture once again, and then thank you for listening.